Yesterday, we looked at how to approximate area under a curve. Today, we are going to look at how to find the actual area under the curve. So, the way we do this is, first of all, realize that you have a function and an x interval from A to B. That's all you have. What you need to do is you need to cut the x-axis up into subintervals. So subinterval 1, 2, 3, blah, blah, blah. Oh. Now, given that this is x sub 1, that means A itself is equal to the x sub 0. And you need to understand that n is a specific unknown constant. N represents how many subintervals we cut this up into. And that means that B is specifically x sub n. Now, as I cut this up into a bunch of subintervals along the x-axis, I have to decide which of the x coordinates within each subsection. So I've got, here's my x, my first x subinterval. I can pick any x on that interval that I want to go into the function. The algebra that you're going to wind up having to do tomorrow, the algebra is much nicer if you choose the right endpoint. But be aware that you can choose any point along that subinterval. And after you guys leave for lunch, I will continue the video and talk more about this particular issue, because I'm probably not going to have time to clarify to you that. So anyway, this creates strips, area strips. So this is giving me an approximation of the area of that first strip. And I'm just going to keep doing that. If I use the right endpoints, I'm going to lob off all these rectangles. And I need a formula for the area of these rectangles. Well, rectangles are made up of height and width. So let's start there. Width. The width of each of these subintervals. Now, I could make these subintervals unequal. It will make the algebra much more complicated. I don't have to make them unequal. I'm going to make my life easier if I decide to make these subintervals exactly the same width. So if I make them exactly the same width, I can come up with a formula for the width that every single one of them has. And that is, what is this entire length? Start with that. How do you find that entire length? That distance along the x-axis. And I'm going to look over to chat for a formula for that distance. Yes, b minus a will give me the distance. If I do a minus b, I will get a negative number that's supposed to be representing distance, so just be aware. And also, whoops, spider. Also, I'm going to name the width delta x. and it is equal to b minus a. And if I cut it up into n equal subintervals, then b minus a divided by n. And that will give me the width of each of these. Now the height. The height of each rectangle is plugging different x's into my function. I first plug x1 in, then I plug x2 in, and so on. So what I'm going to do is I'm going to say that my height is f of, and before I write what's in there, I want to tell you that if I say f of x sub n, I am actually specifically referring to f of b, and that is a specific number. I cannot use the letter n as I go, as I look at my different x's, and I come up with a formula for x sub some number. So I have to use a different letter. And that letter that we end up using is typically I. So let's make sure this is clear. While n is an unknown constant, n is how many subintervals I cut this up into. I is going to be a variable, because I is going to be a variable that starts with 1, goes to 2, moves to 3, moves all the way through until I reach the I value of n. So when I say the height is f of x, I'm going to specify f of x sub I, based on understanding that I is a variable that will go from 1 to n. That is, provided I use the right endpoints. And here's the thing. If I used the left endpoints, then I would have to go from 0 to n minus 1. And if you think about it, that little n minus 1, do you know how much algebra damage it does to formulas? Think about how much that makes a formula more complicated if you have a subtraction in it versus not having a subtraction in it. The crazier the function, the more complicated it's going to be. So we use the right endpoint because it makes algebra easier in the end. Now, the next thing I have to do, though, is I have to figure out, well, what is a formula for the ith x? So what we're going to do is we're going to first say, well, what is a formula for the first x? What is a formula for the second x? And so on. So watch this very, very carefully. This is very important to pay attention to and watch closely. I want to know what is this location on the x-axis. I will have been given a starting a number. Whatever that a number is, all I have to do to get over to x sub 1 is to add something to it that we already found. The width. So my first x is located at x equals A plus the width. And I'm going to use delta x because it would be very painful to sit there and write out the whole formula over and over again. We already have a formula for it. We thought about it and realized it works. And for now, let's set aside that formula and just talk about delta x is a distance. So x sub 2, if I start at A, how do I get to x sub 2? I add the width twice. How do I get to x sub 3? I start at A and I add the width 3 times. Boop, boop, boop. And also realize that delta x is written as 2 letters, but it's only representing one thing. We use 2 letters to be more expressive about what it is representing. But we could have just used the letter H for horizontal distance. And this means I have a formula for x sub I. X sub I is found by starting at A and adding the width an I number of times. And realize that what we're doing right now is a lot easier to make sense of if you only do one thought at a time. Now, we're going to put it together. We looked at width, we looked at height. Now, the area of rectangle number I. So area of the ith rectangle. So I've got area of a first rectangle, a second rectangle, a third rectangle, all the way through to an ith rectangle, continuing on to an nth rectangle. The area of my ith rectangle is the height times the width. Just that, height times width. And I can refer to the formula for width and the formula for x sub I to actually make that expression have only the variables I, n, and then the numbers a and b, and whatever function f of x happens to be thrown in there. Now, I want more than the area of the ith rectangle. I want the area of the sum of all n rectangles. Rectangles. The area of the sum of So the area of the sum of the rectangle areas from rectangle number 1 to rectangle number n. Now, how do I write sum in math? How do I make a big sum? Sigma! Yay! Go Sigma! So I'm going to add together f of x sub I multiplied by delta x, and I'm going to start with I equals 1, and then I'm going to plug in I equals 2, I equals 3, I equals 4, until I reach I equals n. However, that is still an approximation. Because n could be 3. If I try to approximate area with cutting the x-axis up into 3 subintervals, that's maybe not necessarily the greatest approximation. N could be 100. But do you really want to do that? If n is 100, it might be a better approximation. But yet it's still an approximation. Anyone see where this is going? Oh, no, I didn't. Where am I heading with this? We need n to be infinite. And who do we end up bringing into the picture? A good old favorite from the very beginning. Limit. So actual area. The actual area between a function and the x-axis over interval a to b is the limit as the number of rectangles approach infinity of the sum of rectangles numbered I through n, and their area is found by multiplying the function's height times the width, and you can refer to those two formulas. And then remember separately, the width formula is the length of the interval cut up into n pieces. And the ith x to plug into the function is found by starting at a and adding the width I times. Limits always come back to bite us. So this is very, 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 very important. Everything that we do is based on this from now on. The more you understand why this is actual area, the more things we do are going to make sense. Now, I want to show you examples of what you're going to see in your homework and guide you through those. So I'm going to move off of this formula. You can watch the video later if you need it. And the textbook does take you through as well. I've got some little snips of the textbook here that are the most important things to look at. And I'm scrolling slowly, so if you're curious, you can scroll on your own, because I snipped out like the most valuable things to take a look at. And by the way, this is definition 2. They refer to it, but it's basically what I wrote there. Area formula, woohoo! I want to talk about what I have in green after you guys leave, because time will not allow me to talk about that. And you want to be aware of it. All right, here we go. So you are assigned problems numbered 17 through 21 all. And this is not 17, 18, or 19, and this is not 20 or 21. So I made up 2 problems that are not in your homework to show you what you're going to do. And I've got the directions right there waiting to explain to you what it is that they are asking of you. All right, so here we go. Oh, and let me make sure to clarify. Read this carefully. Do not evaluate the limit. That's set for tomorrow. We need an entire other lesson to look at how to deal with the actual math itself. Right now, all we're doing is looking at how to set up the math and where it's all coming from. Here we go. So in problems 17 through 19, you will be given a function and an x interval. And you are to come up with an expression for the area under the graph of f as a limit. And it says to use definition 2. That's basically what I just showed you. So here we go. I'm going to talk you through it. I always start with delta x. And I should warn you, I chose to use as an example something that is harder than what you have on your homework. You'd rather it be that way than the other way. Because take a look at b minus a. You can't just combine pi and 1 unless you use a decimal number, and we're staying away from a decimal number because that's an approximation. So b minus a cut up into n pieces. Pi minus 1 is a number, but we're not able to just combine those two to make a nice looking number that is not a decimal. All right, that's the first thing. The second thing that I do is I get my x sub I formula. My x sub I formula is, I've got a starting number, and I add to that starting number the width times delta x, or sorry, the width times I. So what I'm going to do is I'm going to first just say width times I. Take it a small bite at a time. You do not want to try and lay out this formula in one giant eruption. Unless you want to, some people do. I won't stop you. And now I want to combine these two together. So my x sub I is 1 plus pi minus 1 over n multiplied by I. And that is a mouthful. Now, as I start writing out the actual formula, know that I'm keeping some space to my left because I'm going to talk you through the thought of what we are doing. The thought is I'm multiplying this width times a height, where that height is f of x sub I. So for the height, I'm going to have to take everywhere the variable is sitting and substitute this lovely creature in. And don't worry, you're not going to be asked to simplify it. You're just going to write it in all its lovely glory of complicated messes. So, leaving some space on the left side, I've got, and I'm going to kind of title it also, height, which is the sine of this x sub I formula divided by this x sub I formula again, because, you know, it wasn't bad enough to write it once. Got to write it twice. So there's my height. Height is multiplied by width. And my width is the delta x formula. And realize that that formula is the formula to find the area of rectangle number I of n. There are n rectangles, and this is finding the area of the ith rectangle out of all n of them. I need to add all of them together, and sigma is the one who will do that. So this big, massive mess is going into my sigma. And here's something very important to be aware of. Sigma has only one variable. Sigma needs to add the areas of rectangles numbered 1 through n based on variable I. So I starts at 1, and I then move to I equals 2, I equals 3, I equals 4, until I reach the number n, the unknown number n. And before I write any further, I want you to realize what we have at this point. This now is going to approximate area based on how many rectangles I cut it up into. This is now a formula whose only variable is n. Once sigma takes place, I is gone. I is there for sigma to go 1, 2, 3, and so on. I is gone once sigma is done. Oh, I saw the thing in chat. Sometimes when I talk while I write, I don't write what I intended to write. And correct, I'm only supposed to put an n on top. I don't have to tell it. I tell it the variable once at the very beginning there. I say variable I goes from starting at 1, and then I just throw the n on top. Yes. And so now the only thing left is to make the number of rectangles head to infinity and determine what that is approaching to find the limit as the number of rectangles approach infinity. That will find me exact area. And let's look at what we actually just did. So I've got a Desmos ready. So here I have the graph of sine x over x. I'm going to take a screenshot of it because I'm not prepared to color the section. Probably could have pre-prepared something to make it do it, but I'm going to paste it over here and color. So this is the graph of the function. We were finding the area starting at x equals 1 and finishing at x equals pi. And that formula make that a little bit bigger. That formula is going to find the exact area under this curve down to the x-axis. You know, as I look at it, it seems like this would be so much easier if you just said, you know, it's close to the shape of a triangle. How about I just find the area of the triangle and be done with it? Yes, that would be a lot easier. And know that your purpose is you are trying to understand what integration is. And we've got to go through this to understand what it is. Then we can hit, let's find an easier way. All right. So I'm now going back because you have a second type of homework problem. And that is essentially to go backward from what we just did. We're going to go the other direction. So we had gone from a function over an interval to a limit sigma formula. We are now taking a limit sigma formula and figuring out what is the function and the x interval. Here we go. I'm going to erase a little bit because I need some room over here. Now, do you remember that I started with delta x? I'm still going to start with delta x. Delta x as a formula is length of interval, b minus a, divided by n. And keep in mind my goal is I want to find the function and then a and b. So I will be finding that a and b. Now, how do I find this in the formula? Let's go back over to what we had worked with. Oh, did I really just erase what I was about to use? I did. So what I'm going to do is I'm going to go over to the period 1 where I have it still written. Oh my goodness, that's kind of funny. Let me just find it. Okay. All right, so here it is. Keep in mind that delta x is going to have a divided by n. The a and the b are numbers. And let me just say, for example, if my numbers a and b are 0 and 2, what is my delta x going to look like? It's going to be a nice, pretty number divided by n. What if my interval is 1 to 5? What is my delta x going to look like if my interval is 1 to 5? 5 minus 1 is 4. So another nice, pretty number over n. What if it's a little bit more cruel and it's, say, 0 to pi? Oh, let's go 0 to pi over 3. In that case, my b minus a is pi over 3, and then that is divided by n. But no one's going to write a fraction in a fraction, right? So they're probably going to write it as pi divided by 3n. So understand that what you are looking for is you're looking for an n in a denominator multiplied by other stuff. Then where are you going to find it? One place you are going to find it is multiplied to the entire f of x sub I. So this big mess was our f of x sub I, but that delta x is multiplying to it. And then where else do you see that particular formula? And it's already highlighted, you can see. You should be finding that formula inside of f of x sub I multiplied by I. Because my x sub I formula, just to remind you, is some number plus whatever that delta x is times I. So I am looking for inside, I have this times I. So I'm looking for this times I, and it may show up more than once. So now we're going to go back to the problem we are working on and see if we can find delta x. All right, here it is. So remember, when you're finding delta x, you're looking for an n sitting in a denominator, and it's multiplying, or, with the n in the denominator, there's a multiplication going on. Let me also point something else out to you. Cosine of parentheses is a function. That is certainly not going to be part of my delta x. And that's a whole bunch of what's here. What I see here is a delta x and an f of x sub I. Are you starting to see it? If all of this is my f of x sub I, that would make this my delta x. And what I see there does have n in the denominator. And in this case, what is my b minus a? If my delta x is pi divided by 2n, I could rewrite that as pi over 2 divided by n. And that only tells me so much. It's still not a whole lot. But I can at least say this. My interval starts at some number, but now I have a formula for the number it finishes at. It will finish at a plus pi over 2. So once I've set aside delta x, the next thing I look for is x sub I. And I want to remember what is the formula for x sub I. And I can start off with picture in your head, do not memorize, but picture that you're starting at x coordinate A, and to find your first x sub 1, you add the width once. To get to your second x, you add the width twice. To find your ith x, you add the width I times. And now let's bring in what I found that width to be. And I'm going to write it in this format instead of a fraction in a fraction, because you're unlikely to see a fraction in a fraction in a more simplified answer. So I've got a pi over 2n multiplied by I, so the I is most likely going to show up in the numerator there. And now you must find at least this right here in the f of x sub I. So come over here to what we think is f of x sub I and find exactly this. There it is. Now, for the thing that's going to make you super happy, you have a choice. You get to choose A. And I want you to know that if all else fails, you can choose to make A be equal to 0. And it'll be decent to work with no matter what the problem is. But you're also looking for something that it looks like they're trying to point you towards something directly added to the pi I over 2n. You see some number that is exactly added to it that we probably want to just say, hey, it looks like that's A. Now, you don't have to. But let's allow A to be pi over 2 and see what we get. And I'm going to also show you what happens if you choose A to be 0. So if we make A pi over 2, then that means that my x sub I is pi over 2 plus pi I over 2n. And here's what I want you to do. I want you to find that entire expression. And I'd like to use a different color highlighter, but I'm afraid that might be challenging. So, well, let me see. What color highlighter would be reasonable? Maybe this pinkish? Let's try that. Okay. Nope, it's still yellow. Okay, I don't think I can change the highlighter color. Or I didn't do it properly. Oh, I push OK. Ha, ha, now it's pink. All right. So all of this, find that. Great, now I've got to find that highlighter again. Okay. All right, and then let's highlight all of that. And replace that pink highlight with a big giant X. There's your function. What is the function? The function is cosine x. Because the x variable is going to have the x sub I formula plugged into it. And because I chose A to be pi over 2, then the interval that I am using is pi over 2 2 pi. And this is the answer. This is the region whose area is equal to the given limit, but we're not evaluating the limit. Now, quickly, and we have until 10:50, correct? Okay. If A happens to be 0, if that's what I had chosen instead, then the x sub I that I would want to be highlighting in pink is just pi I over 2n. And I'm going to try and take that pink away. Good. There we go. And let me put it. Oh, yeah, I know. You didn't like that I did that. And you're going to whine and complain to me. Okay. So if I choose A equals 0, then I want to carefully highlight pi I over 2n. And that is replaced with the x variable. And then my function is right there. And do you see what the function is? The function is the cosine of pi over 2 plus x in a parentheses. And that also means the interval is going to start at A equals 0. And what is it going to end at? Pi over 2. And now let's take a moment to see that these are identical. And to do that, I'm going to ask you to think back to some old math classes. If you had a graph of a function, and then you took that function, but you added pi over 2 to its variable x, what did that do to the graph? So what I want you to do is just kind of hold your hands up as if you're holding the graph. How is that changing this graph that you're holding in your hands? And I think I'm seeing, yep. It is horizontally shifting it. Which direction is it shifting it? It's shifting it left, pi over 2. Now, if you look at the interval that my cosine began on, if I shift this interval, pi over 2 to the left, this section of the graph will shift to being 0 to pi over 2. This is the exact same section of a cosine graph. They are identical to each other. Technically, you can make A be any real number you want, but you're going to find that you're either going to use 0 or something that is obvious, that is given. Are you ready now? So that's done. Are you ready for the big connection? Because 2 days ago, we looked at an antiderivative, which, by the way, we're quizzing tomorrow on the formula on doing the antiderivative. Make sure you study those formulas. What does that have to do with area? Well, let's take a look through a familiar function. I have found this to be the easiest way to show this connection because we have worked with this function. If I choose to make a graph for a velocity function with respect to time, and I've put in a bunch of pre-set up lines so that I didn't take as much time with drawing all this out. Now, if I decide to turn this into a bunch of rectangles, And I don't worry myself about what the function represents. Right now, I'm just like, hey, area. How do I approximate area? I add up a bunch of these rectangles. Now, I've got a sample rectangle over here to the right that's waiting. Each of these rectangles has a width. When I go to the fact that this is velocity with respect to time, what is that width? What are each of these individual widths representing? They're representing a change in time. I'm going to put delta t, but this could be, say, 0, 1, 2, 3, and it's in terms of seconds maybe. So each of these widths could represent 1 second of time that has passed. What is the height of the rectangle representing? The height of the rectangle is representing a certain value of a velocity. Now, let's say you're out riding your bike and you approximate your speed and right now I'm temporarily calling velocity speed because we're more used to thinking of speed. So maybe your speed is changing as this velocity. So maybe your speed is changing like how this velocity is changing. But let's say you just approximate that you're going about this fast for 1 second. If you multiply your speed by an amount of time, what did you just find? So we're looking at, first of all, for the non-physics view, speed times time. And keep in mind, speed is something like miles per hour. So I could take miles per hour and multiply it by an amount of time, number of hours, and that gives me miles. Speed times time is going to give me a distance. Now, velocity has the ability to be positive or negative. And if I take velocity and multiply it by time, that gives me what physics thing. Instead of distance, we call it, because distance is always positive, displacement. So what I'm doing is the area of one rectangle is a displacement amount. And if you haven't had enough physics, then let's just say distance. It gives you a distance. So really, I'm adding together a bunch of little tiny distances, and I am getting my displacement over time. What is the antiderivative of velocity? Right. So what you want to think about is when we take the derivative of a position function. So my position function, we had to call it s with respect to t because we couldn't use the letter d. When I look at what is velocity, I am looking at a change in distance over a change in time. what am I doing in finding these rectangular areas? I'm taking a velocity and I am multiplying it by a change in time. That's going backward from taking something and dividing by change in time to now with the rectangle, I am taking a velocity and multiplying it by time to get position. And it is the antiderivative. I want to say a little bit more. First, though, let me explain to you your homework because you are probably going to want to go when it hits 10:50. These first two homework problems are going to be like yesterday. They're asking you to find a lower estimate and an upper estimate. Know that all that's saying is find a left and a right Riemann sum. That's it for both of them. What I want you to focus on is the meaning so that you can make the connection with the area you had been doing before, the area you were approximating by adding a bunch of rectangles up, and how that is the same thing as going backward on the derivative. So this is not, these homework problems are not intended for you to sit here and do the number crunching, although you're going to. But as you're doing the number crunching, think about what it means. And that's the most important thing you can do. So it's 10:50. You can go. I'm going to keep recording and say a few more things that I would have liked to have said to you. And something very, very valuable to talk about that was actually brought up by someone in first period. I'm going to erase a little bit. Yeah. Oh, dear. Okay, I'm just going to start that over. Okay, so I'm just going to get an XY graph going. And then draw something in there. Actually, I should do this. Draw something more like this. And I've got x equals a and x equals b. And if the y-axis is representing velocity with respect to time, and the x-axis is representing time, then one way that I can look at this is, instead of b being a specific number, I can look at it as a variable. And you know, this velocity function could go on and on and on farther away too. So what I'm actually doing with this area is I'm finding out what is my displacement, or in this case, I can talk about distance because I have a positive velocity. So this is telling me, when I add all these areas together, how far I traveled from time A to time B, or maybe time variable. And I can actually look at this as a function instead of just a distance traveled from A to B. I can see this as a variable distance based on a particular distance. I am getting that the area is equal to my displacement, my position at some time x minus my displacement at some time a. And I can take this end of time and move it anywhere I want, and I can actually create a displacement function from this velocity graph based on finding the area with some particular starting point. So let that soak in a bit. And I want to also explain a little bit of what's here because you are going to see your textbook discussing this. I had used right endpoints to come up with that entire limit formula. And we're using the right endpoints because the algebra we're going to see tomorrow is going to be a lot nicer by using the endpoint number being n, not n minus 1. This is, by the way, definition 2 that they refer to, and it's what I showed you. Now, do understand we are allowed to use the right endpoint, but we could use the left endpoint just as well. And all that's going to do is shift my beginning and end x sub I. And as long as we're dealing with a continuous function, it doesn't matter if we use left endpoints or right endpoints. In fact, it doesn't matter what x we end up using in the interval. We just need to, for interval number 1, use one of the x's in its interval. And this is where they have come up with an x sub 1 star. You will see in the future in the textbook, it's going to talk about x sub I star. That x sub I star is referring to the ith x coordinate that is chosen out of the ith subinterval. So we have subinterval 1 picks an x1 star out of all the x values to determine the height of the rectangle. In subinterval number 2, some x sub 2 star is chosen in its interval to determine the height of the function. And then I finally get to my ith subinterval, and I pick some x sub I star. It could be any of these x's to determine the height for one of those x's in those subintervals. And that comes up with these 3 area formulas. So essentially, it's x sub I star, not necessarily just the right x coordinate of each interval. So that's what I wanted to clarify, was that we don't have to use the right endpoint, and that your textbook is going to write x sub I star to represent anywhere from the left to the right x coordinate of each subinterval. All right, so that's it.